Yes, students. So today we are going to see atom. Okay, modern physics. Right. Let's start. In atom, what we have now. Atom we start with Rutherford model. Now we all know what he did. We are not going into that much. Rutherford model. Okay. To discover what kind of thing is atom or what is atom, what he did is he bombarded atom with alpha particles. Okay, we know that, right? So alpha particles are here. Okay, which he is going to bombard. Okay, and here what he took? One gold plate, very thin gold plate. Okay, very thin gold plate. Okay, very thin gold plate means is what is the meaning of very thin gold plate? So that thickness is very less. That means continuous. There should not be too many atoms one behind the other. Okay, very thin plate. How much thin plate? 10 to the power minus 3 mm or 10 to the power minus 4 mm. Like that thin gold plate. Okay, and alpha particles he bombarded from. So what he found is maximum alpha particles goes undeviated from this. Undeviated means is what? Undeviated means is if we talk about now what we know that I am discussing. Okay, like atom's radius. Atom's radius is what? You know that it's 10 to the power minus 10. Okay, and what is the size of alpha particle? Very less. Okay, it's very less. If you say that alpha particle is actually what? Helium nucleus. And nucleus size is what? 10 to the power minus 50. Very less as compared to this. So maximum alpha particles pass through it. That means it's a solid, being a solid, even then they pass through it. Why? Because in every atom there is a lot of space. Okay, so that's why alpha particles were able to cross it. So what he found it, if suppose we make one atom over here and discuss. Okay, so this is an atom, right? And in this one, if you make nucleus also here, well, this is nucleus. Okay, so when alpha particles are bombarded from here, maximum alpha particles pass undeviated. Okay, it's like this. Some alpha particles deviated. Okay, some alpha particles deviated, and we know that how many are deviated. Okay, there is a ratio is there. Okay, so suppose these alpha particles here are deviated. Okay, like this. And we know that one of the particles will return back. This is what the experiment of Rutherford found. So what he said that maximum particles goes undeviated. That means he said that the atom is mostly empty. Okay, atom is mostly empty. Most of the particles go undeviated. Okay, it's point number one. Okay, then 0.14% of alpha particles deviates with some angle. 0.14%. That's all. Okay, 1 out of 8,000 deviates with more than 90-degree angle. Okay, 1 out of 8,000. Okay, deviates with more than 90 degree angle. Okay, and one out of the lot will return back to its own path. Okay, one out of entire lot returns back. Okay, and how we found it? Because after this is actually gold foil. This atom is representing gold foil. And after that, he had another plate. Okay, and that one he had zinc sulfide. So as these alpha particles were striking that one, okay, they were making illumination. So because of that, we were able to find that most of the particles are coming and hitting that ZNS plate. Right? Okay. So this was the finding of Rutherford from his experiment. Okay. Then what he gave, what he concluded. First conclusion, the atom is mostly empty. Okay. The atom is mostly empty. Okay. Second, entire positive charge and mass is concentrated at center. Concentrated at center, and we call that as nucleus. Okay. In nucleus. Third thing he said is electrons are orbiting around the nucleus. Okay, this is all he said. Then what more he was able to find? There are two more things that Rutherford gave us. What was that? One was the impact parameter, and other one was distance of closest approach, from where we were able to find out what is the radius of the nucleus. Okay. So what is impact parameter then? And before impact parameters, if we can go into this aspect, like this is actually the angle theta. Okay. Can we have any relation between number of alpha particles which are going to deviate with an angle theta? Then we have a relation. The relation means is the comparable relation. What is that? This is number of alpha particles, that is equal to 1 by sine to the power 4 theta by 2. Okay. Number of alpha particles which are going to deviate with an angle theta. Okay. Proportionality we have. Number of alpha particles proportional to 1 by sine to the power 4 theta by 2. Okay. So they can ask you that, suppose that 30 degrees and 60 degrees, what is the ratio? We can find. Okay. 30 degree, 45 degrees. In one case, we want to find how many deviated by 30 degrees, and then we know that how many are deviated with angle 45 degrees. So we can do this. Okay, with this relation. So important relation. Right. Now let's talk about impact parameter. So impact parameter is what? Impact parameter is actually the separation, or rather the distance between velocity vector of the alpha particle and the line which is joining the center of that atom. Let's find out what it is. If suppose this is alpha particle here, and this is the line joining the center. Okay, so this is called impact parameter. Impact parameter. And this we represent with P. If this one, then this one is the impact parameter. Okay, so from the line which is joining the center to the velocity vector of the alpha particle. Now here this line is also representing alpha, then here impact parameter is 0. Okay, because this line represents both. center line as well as one of the alpha particle is also going, which is going to retrace its path. So here impact parameter 0, here impact parameter this one, here impact parameter this one. Okay, so do we have any relation or any formula with for the impact parameter? Say yes. Suppose that the kinetic energy with which alpha particle is projected is Ke, then impact parameter relation we have, and what that is? B equal to Ze square cot theta by 2 by Ke. Okay, Z is what we all know, atomic number it is. Okay, E is electron. Cot theta by 2. Theta is the angle of deviation, and this is kinetic. Okay, so this is the relation for impact parameter. But from here, the most important thing that we are going to get this cot theta by 2, I am bringing this side. So 1 by cot theta by 2 means 10 theta by 2. So 10 theta by 2 equal to Ze square by B Ke. Now this gives idea about deviation. Okay, if impact parameter is more, deviation will be less because impact parameter is in denominator. So if you are away from the atom, your deviation is going to become less and less. As you are going away, impact parameter is going to increase and deviation is going to decrease. Okay. Second part is kinetic energy. If your kinetic energy is more, then also your deviation will be less. Okay. If your kinetic energy is more, you pass without getting much deviation. Both things, remember that. Okay. So this is impact parameter. This is impact parameter, and this is relation for deviation. Okay, now let's see distance of closest approach. Distance of closest approach. Closest approach. Okay, what that is? A distance of closest approach means is or alpha particle which bombarded on the gold plate. How close it can go before returning back? That means we are talking about that particle which is going to return back. Okay, how close it could reach? That is what we are going to find with this one. So suppose now this is alpha particle here, which we are projecting with certain kinetic energy, and here is the nucleus because we are going close to the nucleus. So this is nucleus. In nucleus, what is there? Protons are there. Alpha particle is what? Positive charge. Nucleus is positive. Inside, how many protons are there? Let's say Z protons are there. So its charge is, let's say, Ze. Okay. And initially, how far it is? Initially, very far. This distance is infinite. Now you project it with kinetic energy and it goes. Suppose it could reach over. So this distance only we want. This is called distance of closest approach. Now what we can do? We know that when this positive charge is going towards another positive charge, there is electrostatic force of repulsion that is going to retard it. And finally, when it is going to stop, its kinetic energy will become zero. But where that kinetic energy is gone? Since there is electrostatic force or conservative force, energy is conserved. So this kinetic energy will convert into potential energy. That is it. Okay. So what do you do? Conserving energy. Conserving energy means if suppose this is initial position and this is final position, then we can say that total energy at point 1 equal to total energy at point 2. This is kinetic energy at point 1 plus potential energy at point 1 equal to kinetic energy at point 2 plus potential energy at point 2. Okay, so kinetic energy we have at initial position, that is Ke on. This is 0. Why? Because the separation is infinite. Okay, then second position, kinetic energy is becoming 0. Potential energy then 1 by 4 pi epsilon naught. Ze is the charge here. And what is the charge on alpha? 2 electrons. So you can write here 2 electrons by R. This R. Okay, R we want. So finally R value we are getting as 2ZE square by 4 pi epsilon naught KE. 2ZE square by 4 pi epsilon naught KE. This is the distance of closest approach. Okay, and from here only radius of the nucleus Rutherford could give us. Okay, so this is distance of closest approach. Now on this one, let's solve one question. Okay, what is the question? Let's assume that one alpha particle, okay, one alpha particle of kinetic energy K, okay, could go to R naught, closest to gold nucleus. That means distance of closest approach is R naught. Now, same alpha particle, kinetic energy I am saying, make it momentum. One alpha particle of momentum P. Okay, same alpha particle with double momentum. With double momentum is projected. Double momentum is projected. What is its distance of closest approach? What is the distance of closest approach? Okay, this is the question. Simple question. But we should know how to solve it because momentum is not there in our formula. Okay, our formula was related to kinetic energy, right? So what was the formula? Say R equal to 2ZE square by 4 pi epsilon naught KE. Okay, now KE and momentum has some relation. Yes. What is that relation? Kinetic energy equal to P square by 2m. This is the relation. Okay, so we have to convert this into now. So now here it's given that R naught, initially R naught. So R naught is equal to 2ZE square by 4 pi epsilon naught. Now KE I am changing. This P square by 2m. Okay, this for alpha particle. Now this 2Z is constant, E square constant, 4 pi epsilon naught constant. Okay, and this mass of alpha particle is also constant. So actually R, here R is inversely proportional to P square because P only we are changing. Okay, so what we can do? Now I can write it. What we can write? We can write is R naught by R1 will be equal to P1 square by initial, like this. Correct. So now R naught by R1. Now P1 is what? 2P. So 2P means 4P square by P square. This gets cancelled. So R1 equal to what? R1 equal to R naught by 2. Okay. R1 equal to R naught by 4. If you are doubling the momentum, the distance of closest approach is going to decrease. Okay, and it will become 1/4 of what it was earlier. Okay. So this relation we already know, so we used it. Okay, kinetic energy equal to T square by 2m. Okay, then these are the things what was given to us by Rutherford. But Rutherford theory failed. Why it failed? Because it could not give us the logic behind or the reason behind stability of nucleus. Okay, Rutherford could not explain stability of nucleus. Stability of atom, not nucleus. Stability of atom. What was the problem? The problem was it was told that whenever there is a charge which is accelerating, it will radiate energy. So in this case also, electron is orbiting around the nucleus. That's what Rutherford said. Okay, so it is accelerating. So when it's accelerating, it should radiate energy. And when it's radiate energy, that means it loses energy every time. So when it loses energy, that means ultimately its radius keeps on decreasing and finally it will fall in the nucleus itself. Okay, that was a question asked from Rutherford and Rutherford could not give its answer. Right, so that is why Rutherford theory failed. But is it failed totally? No. Okay, many things we took from Rutherford theory only. But this particular thing was then explained by Niels Bohr. Okay, so what is Niels Bohr theory then? Niels Bohr theory. Okay, what he said? He said that the electron which is orbiting around the nucleus, its energy is constant. Electrons orbiting around the nucleus in constant energy orbits. Okay, electrons are orbiting around nucleus in constant energy orbits. Constant energy orbits. That means they are not going to lose energy. Point number one. Second point, he said is angular momentum. Angular momentum of orbiting electrons okay is equal to nh by 2 pi. N is what? What is n? It has to be a whole number. Okay, and it is the which shell they are orbiting, that n we are taking. Okay, so angular momentum of orbiting electron is equal to nh by 2 pi, whole number multiple of h by 2 pi, where h is Planck's constant. Okay, and what is n here? Quantum number. Okay, n is, or you can say that the shell, which shell the electrons are orbiting. Okay, shell of orbiting electron. Right. Then this is angular momentum of orbiting electron. Third, then he said that if electrons are moving from higher energy orbit to lower energy orbit, if they are jumping one shell to another shell, then only exchange of energy takes place. If they are moving from higher energy to lower energy orbit, they will release energy. Okay. When electron moves from higher energy orbit to lower energy orbit, then there is release of energy. Then there is release of energy. Okay, this in addition to what Rutherford said, Niels Bohr said. Rutherford was failed only in this aspect. So Niels Bohr considered that, he said that electrons are orbiting in constant energy orbit. So there is no point of electrons losing energy while orbiting. Second one, angular momentum of orbiting electrons, MVR. Angular momentum is what? L. L is equal to nh by 2 pi. And when electron moves from higher energy orbit to lower energy orbit, then there is release of energy. Okay. So fine. Right. So this was concluded. Angular momentum we represent with L, which is actually MVR, that's equal to nh by 2 pi according to Niels Bohr. Okay, Now let's talk about the electron which is orbiting. So we know now that they are orbiting in circle, right? And there is nucleus here, and this is radius of electron. So that is R. Okay. Now if it's rotating in this one, then it must have a centripetal force. Then only it's possible for electron to move, right? Let's say electron is moving like this with velocity. So we know that centripetal force, its value will be mv square by r. Here m is mass of electron. So who's providing a centripetal force? We will say that the attraction force of nucleus on the electron. So what is the attraction force? So 1 by 4 pi epsilon naught. Okay. Now how many are there? How many protons are there? That is only going to attract this electron, say Ze. And here is charge E. Say Ze square by R square. Okay. R gets cancelled. So mv square value we got. From here we can find what is the kinetic energy of electron which is orbiting. Okay, kinetic energy means half mv square, right? So half mv square we can do here. Half mv square equal to Ze square by 8 pi epsilon naught r square. This is kinetic energy. Kinetic energy of electron is Ze square by 8 pi epsilon naught r square. Same way we can find potential energy. Potential energy is what? 1 by 4 pi epsilon naught Q1 Q2 by R. Q1 is what? Ze. Q2 is E by R. Now potential energy will be positive, negative, negative. Because one charge is positive, other charge is negative. Attraction force, so potential energy negative. Ze square by 4 pi epsilon naught R. Ze square by 8. One R is extra over here. Yes, here. Because we cancel this R. So here still I am writing R, so this R will cancel. Okay. So Ze square by 8 pi epsilon naught R. Here is Ze square by 4 pi epsilon naught. So potential energy is double of kinetic energy in magnitude. Or you can like this, minus of 2 times kinetic energy. What about total energy then? Total energy will be sum of both. Total energy, which is potential energy plus kinetic energy. Okay, when you are going to add both, it is going to come minus Ze square by 4 pi epsilon naught R. That means total energy is magnitude Ze square by 8 pi epsilon. Okay, so total energy is magnitude is same as kinetic energy is magnitude, but this is negative. Okay, so total energy is half of potential energy, and total energy is equal to minus K. Important relations, right? So this we know about total energy. Fine. Then what about its radius and its velocity? Do we have any relation to them? Yes, we have that also. So from here only, we know that mv square equal to 1 by 4 pi epsilon naught Ze square by r. Okay. One more time we'll write it. So mv square by r equal to 1 by 4 pi epsilon naught Ze square by r square. Okay. Then we have another relation which says mvr equal to nh by 2 pi. This is one relation, this is second relation. From here we will be getting value of r as well as v. Okay, so from here we know that r is cancelled. Okay, now if I am going to keep here v in terms of r, we will be getting r value. So what is v in terms of r? Say v equal to nh by 2 pi mr. This I am going to keep here. This is m, n square, h square by 4 pi square m square r square equal to Ze square by 4 pi epsilon naught r. This r and this cancel. Now r value we want. Can we get it? Yes, we can get it. We take r over here and bring everything over here. So 4 pi epsilon naught n square h square by 4 pi square m ZE square. That's equal to R. Whatever things you can cancel, we can cancel. This 4 pi is cancelled. This 4 pi is cancelled. Anything else we can cancel away. That's all. So epsilon naught n square h square by m z e square. This is R value. When you can see that in the epsilon is constant, Planck's constant, mass of electron constant, and electron's charge is constant. So when we are going to keep this all, we are going to get R equal to 0.53 angstrom n square by z. So do we have to remember this? Yes, should remember this, and we also should remember this. Sometimes they ask you this formula, this particular thing, not formula, I should not say formula, but they ask you this. N square by z we know from here, there is no doubt about it, but remaining thing also they can ask you. So this is about radius. Same way velocity. See velocity here. Okay. Now once you got radius, what we have to do? I have to place it over here. That's it. So velocity value is nh by 2 pi m into r. Now this is r. Okay. So epsilon naught n square h square. Epsilon naught n square h square by pi m z e square. Pi z m e square. Okay. What we can cancel in this one? This pi gets cancelled, m gets cancelled. That is it. 1h gets cancelled. So what is here? Constant. Z is constant, e square constant, epsilon naught constant. So if you keep their values, it comes out to be c by 137, z by m, or 2.2 into 10 to the power 6, z by n meter per second. Okay, this is v, the velocity with which particle is orbiting. So here radius is 0.53 angstrom n square by z, v is 2.2 into 10 to the power 6 z by n. Okay, same way time period also we want. What is time period? Let's see. Time period. Time period is what? 2 pi r by v. Okay, 2 pi r by v. Now, what we want in this one? We want value also exactly we can find. But now we want proportionality. Proportionality. You can say radius is proportional to n square by z. Radius is proportional to n square by z. This is constant, right? N square by z. And velocity is proportional to z by n. So what will be the proportionality? N square by z by n. T is proportional to n cube by z square. Now on this one there are many questions. Many questions are there. Okay, if they change the which shell it is, change the z, and they will ask you T1 by T2. They can. Same way velocity also, they can ask you radius also. But this is for time period. Then what? One more parameter is there. This is third, right? Fourth parameter is angular momentum. Now, angular momentum in one way it is easy. Why? Because angular momentum we know is nh by 2 pi. So L is directly proportional to n. You don't have to do anything. Because h is constant, 2 pi is constant. You don't have to keep velocity in this one and then r and then find out what is the relation. It's directly given to us. MVR equal to nh by 2 pi. So L is directly proportional to n. Then there is one more factor, that is magnetic moment. Now, magnetic moment is what? I into A. Okay. We represent this with capital M. So this is equal to I into. Now I, for that I also you should talk, right? Okay, we forgot to talk about I. Fine, no issues. Okay. So here it is. So I. Now I basically is Q by T or E by T. Okay, and time period we already know. Here it is. Time period is proportional to n cube by z square. Here time period is in denominator. So I is proportional to I is proportional to z square by n cube. Z square by n. That is I. And then the area is pi r square. So if we are going to talk about m is proportional to z square by n cube, yes, into r square. Now r is proportional to n square by z. So n square by z whole square. Okay, what we are getting? M is proportional to z square by n cube into n to the power 4 by z square. This cancel and this cancel. So magnetic moment is also proportional to n. Angular momentum is also proportional to n, and magnetic moment is also proportional to n only. Okay, then one more factor we can do. What? Magnetic field produced at the center, because electron is rotating, right? So magnetic field produced, that also you see. Magnetic field produced. Now these all relation that we are getting, how the questions will be asked you, they will change the values, n value, z value, and they'll ask you the ratio. So you should know all this, okay? Magnetic field at center. What is magnetic field at center? Mu naught I by 2r. Okay? Magnetic field at center is what? Mu naught I by 2r. So if you are searching the proportionality, then V is proportional to I by R. I, let's go back. Check what is I. I is proportional to Z square by N cube. Okay. Okay. So V is proportional to first Z square by N cube. Then there is R. R is proportional to N square by Z. So V is proportional to Z cube by N to the power 5. Okay. Z cube by N to the power 5. Okay. So these are all parameters in which we can show the proportionality, and we can find the questions which are related to ratios. Okay. This is magnetic. So this is how you should be able to find. What is the main thing in this one? You should know radius, how radius is varying. Second thing, how velocity is varying. These are very, very important. Remaining all are built on them all. Correct? Okay. Now let's talk about energy. Energy, we already have the relation. We already found one relation for energy. There is that. Here. We discussed about energy already. This is the energy. Okay. Total energy is minus Z square by 8 by epsilon naught R and all that. Okay. But now we have to keep the value of R in that form so that we can get the final relation. Okay. So total energy is what? Minus Z square by 8 by epsilon naught R. Okay. Let's see. So total energy here. Minus Z e square by 8 pi epsilon naught R. Now I want to keep R value. What is R value? R value we already have found. This is R value here. Okay, what is that? N square h square epsilon naught by pi m Z e square. Okay. N square h square epsilon naught by pi m Z e square. Let's see whether I remember it or not. Okay, so let's keep it here. R is equal to N square h square epsilon naught by pi m Z e square. Let's check once. N square h square epsilon naught by pi m Z e square. Perfect. Okay, now this value of R I am going to keep here. Now see total energy minus Z e square by 8 pi epsilon naught R value N square h square epsilon naught pi m Z e square. Okay, anything we can cancel, we will cancel. So this pi and pi gets cancelled here. That's all. Yes. So what we have, minus m e to the power 4 z square by 8 epsilon naught h square epsilon naught square 8 epsilon naught h square n square. Now again you see that this thing is constant. So this total energy that we remember, what is our important for us, that is minus 13.6 eV z square by n square. Minus 13.6 eV. This is an electron volt. Z square by n square. Okay, and we remember this. This is the total energy of electron which is orbiting in any orbit. The shell number is n, and this is atomic number. Correct. Now, one more thing that we have not discussed so far is Bohr's atomic model is only applicable for one electron atom. Okay, one electron atom. That means in that one electron is left. We cannot apply this when many electrons are orbiting around the nucleus. Okay, it is only applicable for hydrogen-like atoms. Bohr's model is applicable only on hydrogen-like atoms. Okay, so what is the total energy we are getting? Minus 13.6 eV z square by n square, right? So then what we can find out? We can find out what is the energy of the electron in all the orbits that we have. In the first orbit, we can say very easily minus 13.6 eV, if suppose we are talking about hydrogen atom. Okay, first orbit for hydrogen atom. Okay, so what it is? Minus 13.6 eV, because Z is also 1, N is also 1. Second orbit, minus 13.6, Z is 1 and N becomes 2. So it becomes 3.4 eV. Okay, third orbit, minus 13.6 into 1 by 3 square, that is minus 1.51 eV. Like this, we can find very easily with the formula that we have, minus 13.6 z square by n square eV. But as you see that, if as the shell number is increasing, the energy is also increasing. This is the minimum energy. Minus 13.6 eV is minimum energy. It's minus. Okay, this is more than that. This is more than that. Further, it will be more. But what is happening? You see, the difference in energy over here is a lot more than the difference in energy over here. That means, as you are going up, difference in energy is going to decrease. And radius of orbit also will be coming very close to each other. As you go up, higher energy orbits and higher energy orbits, energy difference is decreasing, so is the radius difference. Okay, fine. And finally, how much? What is the highest energy we have? 0. Okay, we will have 0 energy. Then we will say that after that it is going to ionize. That is ionization energy. Ionization energy means what? If you are able to take electron to 0 energy, then we will say that that particular atom is ionized. Okay, so if suppose that the electron is here minus 13.6 eV, from here you give certain amount of energy so that the final energy becomes 0, then you ionize it. So how much energy we have to give? Plus 13.6. So ionization energy is plus 13.6. Okay, right. So leave at the moment, ionization energy will come back again. So here is what we are saying, as the energy of electron is increasing, the radius of orbit, not a radius of orbit, the difference, no, not this, not like this. Okay, as electrons energy increases, difference in energy between shells decreases. Okay, so as radius difference. Okay, as you are going up, the radius also, the difference in radius also keeps decreasing. That means at higher energy orbits, the shells will be very close to each other. Whereas in the lower energy orbits, shells will be separated. You can see them clearly, but in higher energy orbits, they will be very close to each other. Okay, so this is the energy thing. Now, if suppose that how the question will be asked, very simple question will be asked from you. They'll compare two types of atoms. Suppose if try and frame one question on this one. Okay, try and frame one question. So, what type of questions we can get it? Okay. Suppose energy of for hydrogen. Okay, hydrogen atom. Na? Energy for hydrogen in second orbit is E. Okay, then fine energy for helium plus in second orbit. Like this question will be asked. Okay. In hydrogen's case, in second orbit energy is E. Then in helium plus, what is the energy in second orbit? What you'll do? Question is simple. For hydrogen first, so we know that total energy we write as minus 13.6 Z square by M square EV. Now, when we are talking about hydrogen, that is minus 13.6 into 1 by 2 square. And this is what we are calling as given. Okay. Then for helium, okay, singly ionized atom. So total energy in this case what will be? It is E1 minus 13.6. Now what is Z for helium? 2. This is 2 square. By N. N is what? How much? Second orbital. So 2 square. This is coming minus 13.6. So if this one is saying is E, then this is how much? This is 4E. Correct. 13.6 by 2 square only is calling E. So what we multiply here 4. We are calling this is 4. Okay. This kinds of relation. They can ask you helium in the second orbit, or third orbit, or fourth orbit, or fifth orbit. Like this, they can ask you the relation between them. Okay. All right. Then what else we have in this atom? Then there are two types of spectrums. Okay. What spectrums are there? There are two types of spectrum. Absorption spectrum and emission spectrum. Absorption spectrum. Now, absorption spectrum means what? Absorption spectrum means if suppose that we are going to have certain kind of radiations coming from one side. Radiations means is known radiations. or you can say that there are certain photons are coming. Okay, the photons are bombarded from this side. These are photons of possible all kinds of energy. Okay, they are coming, or I'll show it like this. With the arrows, we'll show. So photons are coming in this way. Okay, like these are coming. A few more we'll make possible. Let's try. Okay, so these are how the photons are coming of various energy, and we know all energy. And in this zone, we have a gas. Okay, keep a gas over here. This is gas over here. Now, what will happen is this gas is going to absorb these photons. Okay, which photons it is going to absorb, which it requires to get excited. Excited means is where electron is going to move from lower energy orbit to higher energy orbit, and there is a fixed energy gap between them. It's not that all the energies it can absorb. No. Okay, when we have to move from n equal to 1 to n equal to 2, there is certain energy gap. N equal to 1 to n equal to 3, certain energy gap. N equal to 1 to n equal to 4, certain energy gap. So whichever energy gap is fitting into the energy of photon, they will absorb. So what will happen when we are going to project this all on this screen? Are we going to get all the photons which were emitted from this? So we'll say no. There will be certain photons will be missed from here. Which photons will be missed? Which are absorbed by this gas. And what types of photons this is going to absorb, that we know, because we know about the gas. Okay, so the missing photons in the spectrum is called absorption spectrum of this particular gas. Okay, this is the gas. Okay, so all will not reach. So suppose certain one I am showing you. Okay, suppose this reaches, this reach. Okay, this reach, and finally this one reach. Okay, so 1, 2, 3, 4, 5, 6. This represents the absorption spectra of the gas because these did not reach. Okay, this is absorption spectrum. Spectrum of the gas. Is this the characteristic of the gas? Answer is yes. Every gas is going to have different absorption spectrum? Yes. Because for every gas, or for every atom rather, you have different energy gaps between the orbits. There are no two gases or no two atoms in which the energy gap will be same. So we are not going to get absorption spectrum same for any atom or any gas. Okay, clear? This will absorb only those photons which are falling into the energy gap of two orbits of any atom. Now, energy gap can be for n equal to 1, n equal to 2, n equal to 1, n equal to 3, n equal to 1, n equal to 4, n equal to 1, n equal to 5, like that. Okay, those are only it is going to absorb. So it will be characteristic of that particular gas. Exactly same way is emission spectrum. Now, emission spectrum, when it happens, when electrons or atom is already excited. Okay, when excited electron is going to come to ground state, or it is going to de-excite, then it is going to release the photon. Okay, during de-excitation, of atom, it releases photon, releases energy. This This is called emission spectrum. This is called emission spectrum. Is emission spectrum also characteristic? Answer is yes. There are no two atoms which are going to radiate the same kind of energy. Okay. So what in this one we are saying that it is de-excitation. Now de-excitation means is suppose that if it is going to de-excite from n equal to 3 to n equal to 1. So what happens in that? Okay. So if we say n equal to 3 to n equal to 1. This is n equal to 3. N equal to 2. N equal to 1. So what are the possible photons it can release? Maybe it is going to de-excite with n equal to 3 to n equal to 2. Is for every atom n equal to 3 to n equal to 2 same energy gap? Answer is no. So it is again characteristic. N equal to 2, n equal to 1. So there is a possibility that it can release 2 photons or it can jump directly. It can jump directly. I am talking about single atom. In a single atom. In a single atom, if it is going to de-excite from n equal to 3 to n equal to 1, what are the maximum number of photons it can release? 2. Minimum number of photons? 1. But if we talk about gas, in a gas, now in a gas what will happen? In a gas there will be many atoms. Many atoms will be there. So what are the possible number of photons we are going to get in that gas? There is 3. This also will be there, this also will be there, this also will be there. Some will be coming in this, some atom will be de-excited in this way, some will be de-excited in this way. So here possible number of photons will be what? 3. So now see that what the answers are. Sometimes you get confused in this itself. This is a single atom. Okay. Maximum number of photons possible. 2. In this one, possible number of photons received. 3. Single atom 2 maximum. 1 is also possible. Not that 1 is not possible. 1 is also possible. We are writing maximum. Minimum number if you have to ask, then 1. But in this one, all 3 are possible because there are many atoms. So many atoms, we don't know how they are going to de-excite. So we are going to get there 3. Which one? N equal to 3 to n equal to 2, n equal to 2 to n equal to 1, and n equal to 3 to n equal to 1 also. Okay. Alright. Suppose n equal to 4. From n equal to 4, they are going to jump in a gas. In a gas. Okay. If they are going to jump from n equal to 4 to n equal to 1, then how many possible number of photons? Possible number of photons we find with the formula. What is that? N into n minus 1 by. You can find directly from here. Okay. Minimum energy photon will be for n equal to 4 to n equal to 3. Maximum energy photon will be n equal to 4 to n equal to 1. That also you should remember. But how many total number of photons possible are? N into n minus 1 by 2. But sometimes they will be asked from you that if it's not jumping from higher energy orbit to ground state directly, but it is going to be like first excited state or second excited state, then see, if electron jumps from n1 to n2, then possible number of photons. So see what I am writing, n1 minus n2, just like here is n minus 1, from n to 1 it is jumping. n to 1. So here I am writing n1 to n2. And here is what then n. So that means this is n1 minus n2 plus 1. Right. This is how you can remember. Okay. This is n1 minus n2. This n minus 1's place I am writing n1 minus n2. And this is what? N minus 1 plus 1. This n is n minus 1 plus 1. So what you have written n minus 1? N1 minus n2. So n1 minus 1, n2 plus 1. These are the possible number of photons. If electron is jumping from n1 to n2 in a gas, not in single atom. In single atom, this is not possible. Okay, clear? Okay. This is what about emission spectrum is there. Again, absorption spectrum and emission spectrum both are characteristic of the gas. Remember that. Okay. Now then, we didn't talk about excitation states. No. So let's talk about excitation energy. So excitation energy, we know that if we're talking about an atom, let's talk about an atom now. This is ground state. This is ground state. Okay. All right. One more will take. One more. Okay. Major size. This is first excited state. Second excited state. And there is third excited state. Actually, the radiation difference should decrease. Still, it is considerable. Yes. Okay. Here also it should decrease. Okay, fine. So this is how it is. Now this is ground state for us. This is first excited state. This is second excited state. And this is third excited state. Okay, ground state means n equal to 1. First excited state means n equal to 2. This is n equal to 3. And this is n equal to 2. So sometimes they will not give you n equal to 1, 2, 3, 4. They will talk in terms of excited state. Okay. So excitation energy means what? When you are going to send electron from here to here, that's excitation energy. Okay. From ground state to first excited state. First excited state. So how much energy is required? You have to give the energy. Absorption spectrum, let's talk about. And you are exciting it to from ground state to first excited state. So how much energy is required? The delta E. Final energy minus initial energy, what is? Okay. So energy of n equal to 2 minus energy of n equal to 1. So what we have here, minus 13.6 z square by 4 EV minus 13.6 z square by 1 EV. You can see that it will come positive. Okay, what is it? 13.6 3 z square by 4. Okay, that means EV. This is excitation energy. That means how much energy you give so that it is going to move to the higher energy on. Maybe you are exciting from ground state to n equal to 2, ground state to n equal to 3, ground state to n equal to 0. If ground state to n equal to 0, it becomes ionization. Okay? Ionization energy. ionization energy. What is it? If energy is given so that electron excites to n equal to infinity, then the energy is called ionization energy. So how much energy we have to give if we are going to send it to infinity? This is infinity. Infinity means that this entire thing will become what? Zero, because it's square by infinity. This is zero. So zero minus ground state energy, suppose. Correct. Ground state energy means minus 13.6. I'm writing it this. Ionization energy. Okay. So what it is? Energy at n equal to 1, final minus initial, n equal to infinity minus energy at n equal to 1. So energy at infinity is 0 minus 13.6 z square by e square, z square by n square. So n is 1 anyhow, so no need to write. What are we getting? It is 13.6 z square. For hydrogen it is 13.6 eV for hydrogen. That is ionization. Now sometimes they ask you ionization potential also. What is ionization potential? Ionization potential means with what potential difference we accelerate the electron so that it jumps from ground state to n equal to infinity. Okay, that is ionization potential. Ionization potential. So nothing here, this ionization energy is there. No, that I am going to write as Q delta V. Okay, so how much potential difference through which we run the charge or electron for that matter, not the charge. Okay, electron, so that it acquires ionization energy. Okay, with how much potential difference we accelerate the electron so that it gets ionization. So that means we are going to equate this with this one, 13.6 eV, and this is cancelled. So how much is the potential difference? Ionization potential, that is 13.6. Okay, this is minus 13.6 volt. This is called ionization potential. Whatever is ionization energy, same is ionization potential, but its unit is volt and here it is eV. Okay, fine. Right. Now we'll talk about lambda, wavelength. What is the wavelength of photon when a photon is released? Suppose emission spectra is there. Okay, if it is jumping from n equal to 1 to n equal to 2 or moving from n equal to 2 to n equal to 1, then the photon which is exchanged, what is its wavelength? How to find it? Very simple, that is again. So here if we suppose excitation energy is there. Excitation energy. Excitation energy means it has to absorb the photon, then only it is going to excite. Okay. So energy at n equal to 3 minus energy at n equal to 1. Okay. For hydrogen only we are talking now. So minus 13.6 by 3 square minus 13.6. That's all. By 1 square. Right. So this is energy V. Now if suppose I want to find out that what is the wavelength corresponding to this energy, what I have to do? I have to equate this with hc by lambda. Okay, energy of photon in terms of lambda. or I need to equate it with h into frequency. Now this is how the energy of photon is written, either h nu, h into frequency, or hc by lambda. This is equal to this. Okay. Now what we are getting here? 13.6. This is 1 by 9 minus 1. So that is 8 by 9. But remember, this is in EV at the moment. We want exact value because this is in Joule. So we have to keep here electrons charge 1.6 into 10 to the power minus 19. Then it's perfect. Okay. Okay. So this is HF or Hc by lambda. This is how we can find the wavelength related to photon. That this much particular wavelength is required to send an electron in a hydrogen atom from 1 to 3. Okay, n equal to 1 to n equal to 3. Exactly same way, if suppose that electron is jumping from n equal to 3 to n equal to 1, how much energy is going to be released? Again same thing. Okay, if you want to find out what is the wavelength of photon, equate this energy with this one, we will be getting the wavelength of photon or maybe frequency of. Right, but one more formula is there directly that we can apply. Okay, what is that? For wavelength, if suppose we know that it is jumping from this orbit to that orbit, that is 1 by lambda equal to rz square 1 by n1 square minus 1 by n2 square. Okay, this is direct formula. In this one I don't have to convert electron volt and other things. But in this one this r is there. What is this r? Okay, what is this r value? It's 1.09 into 10 to the power 7. Okay, R value is 1.09 into 10 to the power 7 per meter. Right, how it came? Then this thing we are going to keep again into the formula way, how 13.6 EV came. Okay, that again, that same formula we are going to keep. From there, we are going to get a constant, and this constant is we are getting. Okay, so its value is 1.09 into 10 to the power 7 per meter. So 1 by lambda equal to rz square 1 by n1 square minus 1 by n2 square. Okay, now what more is there in atom? In emission spectrum, we have a series that we have to remember. When electron jumps from one energy orbit to another energy orbit, we said that photon is released. Now that photon will be belonging to one emission spectrum, one emission series. That what series is? Emission series. Okay, so we know that it is actually Lyman, Palmer, Arschen, Brackett, and T5. Lyman means is what? If the electron is jumping to n equal to 1, ground state, then the photon release belongs to Lyman series. See, if suppose we show it like this. This is a ground state. 1, 2, 3, 4, and one more. Okay. This is here. And this one. Like this. Okay, and in between maybe many more energy orbits are there. Okay, this is n equal to 1, n equal to 2, n equal to 3, n equal to 4. Okay, one more we should make, right? One more. Okay. So when you are talking about Lyman series means what? Lyman series, let's say we show with green color. Okay. So electron is jumping from n equal to 2, n equal to 3, n equal to 4, n equal to 5 or n equal to infinity. These all are Lyman series. This is Lyman. Balmer means is it's going to jump to n equal to 2. Okay, these are Balmer. Now, how to get the energy we all know. Okay, what energy is coming, what wavelength is coming, how to find it we all know. That's why I'm not telling you that now because we have discussed it. Okay. Then when we talk about Paschen, Paschen means is it will be coming to what? It will be coming to n equal to 3. So this is Balmer. This is Balmer. This n equal to 1 here, this is n equal to 2. Now we are going to talk about Paschen. Paschen means n equal to 3. That means electron will jump like this. Okay, this is Paschen. Then let's talk about bracket. So bracket means here the electron is going to jump in this way. This is bracket. Okay, then finally this paper. So this is emission spectrum. Okay, when you talk about Lyman, that means when the electron can be from anywhere, it jumps to n equal to 1, belongs to Lyman. Then if it is jumping to n equal to 2, it belongs to Balmer. Then this is Paschen. This is bracket. This is bracket. Okay, clear. Now in this one, Lyman belongs to ultraviolet series, ultraviolet range. Balmer comes in visible. This is infrared. This is infrared. This is infrared. Okay, ultraviolet, visible, infrared. So this is emission spectrum of hydrogen-like atoms. Okay, how to find the energy? We already have discussed. This is the way we find the wavelength of photon, and this is the way we'll find energy difference. Correct. So this is what we have in atoms theory part. Okay. Then we have one de Broglie's theory. Okay. So de Broglie said what? De Broglie actually helped Bose to establish its second postulate. What was second postulate? MVR equal to NH by 2 pi. Okay. De Broglie hypothesis. De Broglie hypothesis. Okay. So de Broglie only helped in achieving that second hypothesis or second postulate of Bose. What was that? MVR equal to NH by 2 pi. Remember that. Okay. But other than that, what de Broglie said is the wavelength is actually also associated with mass. If any particle of mass m is having motion, it's having momentum, okay, then it is also creating or generating energy or radiating energy, and its wavelength he has given as lambda equal to h by p, where h is Planck's constant, p is momentum. So lambda equal to h by p. This is matter wave. Why matter wave it is called? Because it's related to mass. So matter wave. Is this also applicable to photon? Yes, it's also applicable to photon. Lambda equal to h by p is also applicable for photon. Okay, and photon is also considered to be having mass. Photon's rest mass is 0. The rest mass of photon is 0. So at rest, it doesn't have any wavelength. But when it moves, it is having mass. It carries energy. Okay. So lambda equal to h by p. This is matter wave. Now p, we know that we can write it as 2mke also, root over 2mke. So same lambda we can write as like this. Okay. Now this kinetic energy we can give to charge also. If we are going to accelerate with certain potential, then we can write the same formula like this also. Q into delta. A charged particle will be either electron will be there or maybe alpha particle is there, right? So we can have like this one. Okay. So it is 2m into Q into delta V. But if suppose that we are going to give kinetic energy with the help of temperature, okay, then what do you say? In that case, kinetic energy how to write? Because velocity we used to say is how much? Root 3 RT by m or 3 kT by m. So half mv square. How we'll say? Kinetic energy is half mv square. Half m 3 kT by m. Okay, m gets cancelled. 3 kT by 2. So here, in place of kinetic energy, we can write it as root 2m. Then here, d by 2. So remember that. Okay, if we are talking about thermal energy, then we can represent it in this way. So these are all the formulas for lambda for different particles which are moving in different ways. This is simple kinetic energy if it is given. This is in terms of potential difference. This is in terms of temperature. So this is how we can do, or we can find out the wavelength associated with matter wave. Okay, clear? Okay, so wavelength we found, and this is also valid for photon. And photon's energy, how we write? Hc by lambda or h into f. Right, in terms of that also we know, right? E equal to mc square. So E equal to p into c. So momentum of photon is this. This for photon only. Okay. So this is for photon, this is for particle like electron, as I said, electron, alpha, deuteron. We can associate them and we can find wavelength for those particles as well. Okay. So this is what we have as far as atom is concerned. Very simple chapter. Nothing much is there, but only thing is you should have a clarity of all the things. Right. Certain numericals are there. I am going to post it. Okay. But here we are finishing today, but I am going to give you certain recordings today. Okay, related to the numericals on this topic, and then what is that? Nucleus. Okay, and photoelectric effect. Okay, small topics are there. Recordings I will be posting it today along with this one, and tomorrow we will finish with semiconductors. Okay, students. So all right, students. That's all for today. Okay. Thank you. But before that, take the QR code, scan it. Scan QR code so that it helps you when you are going to read it. Okay.